problem number 5000. In this problem, I would like to introduce you a concept of vector function in an n-dimensional hyperspace. So I would like to get started with a simple case when we have just a function. This is going to be a vector function, which is defined as follows. It is essentially the mapping from the scalar real numbers field into n-dimensional vector space over the field of real numbers. For anyone who knows, the field of real numbers is essentially the abelian commutative group closed under operations of multiplication and addition. I'm not going to dive deep into this, but it's going to be useful here in this application. So how is this function defined? So this function is defined the following way. For any scalar value which belongs to the field R, there exists some vector. Well, let's call this vector y for this case, and this vector y belongs to the n-dimensional vector hyperspace, and it is essentially by definition the result of f taken at t. What is this function defined? So this vector function, as defined in n-dimensional hyperspace, it defines a set of points, or a hyperset of points here in the hyperspace, which is the hypercurve. Well, that's just like a curve in the three-dimensional space. It's just a hypercurve in an n-dimensional vector space. This is interesting. This function depends only on one scalar value. That's why it becomes a hypercurve. It is not a surface, it is the curve. You can treat t scalar value as some sort of time. It's not a time in general sense, because there is no time in mathematics, but it's a useful abstraction, useful conceptual model, which can help you intuitively understand the scope of the problem, like in a more intuitive, more efficient way. Now, what is this vector y? So this vector y, as defined by definition, it is the product of, well, it is the image, it is the result, it is the value which belongs to the image space of this vector function, or it's kind of belongs to the codomain as well. But we can also highlight that this is the vector. Since this is the vector function, result is the vector, it can be referred to as a vector, where each component is the result of some function, is the image of some function, f1, f2, until fn, because this is n-dimensional space. So this is, I'm going to highlight T transpose belongs to Rn, because this is kind of the space of vector columns. So what is the fj, fi in specific case? So what is the fi or fj? Let's call it fj of t. This is the scalar function from the field R into the field R. So generally speaking, we can consider the function f, which is the vector function in n-dimensional hyperspace, the following way. For any scalar belonging to the scalar field R, we can apply many scalar functions f1, f2, and then until fn, and all of them are individual scalar functions. Each produces the value y1, y2 until yn, and each one by definition is the result of this. It belongs to the image of f1, the same to f2 of t belongs to image f2, and until fn of t belongs to image fn. So this is essentially the package containing very different scalar functions, each returning a component of the resulting vector. So our vector function in n-dimensional hyperspace can be decomposed into individual scalar functions, each defined with respect to the values t in the according scalar field R. Nice. So what kind of application can we get from this? What can we get out of this? So one of the main and most interesting conclusions is the derivative of this function. If we have the function defined as follows, let's designate this vector y as the result of ft, which is the vector as we defined f1 of t until fn of t, transpose. What is the derivative of this function? If we would like to find the rate of change of this function with respect to this variable t, with respect to this time abstraction, with respect to this time abstraction time, kind of. So in this case, if we want to find that this is going to be a differential f over, well, with respect to the scalar variable t, let's prove that this is the following vector d of t, d1 of t, right? With respect to t, df2 dt with respect to t, and so on. This is the vector in n-dimensional hyperspace, and t, which is also transposed and belongs to Rn. Sometimes they call it the functional derivative of, well, in this case, it's kind of just the vector which is collinear to the hypertangent to this hypercurve. It is not a unit vector, but it is collinear to the tangent line, a tangent hyperline. So how to prove this? Well, if we actually want to prove that, we need to decompose this vector a little bit. So by the definition of limit, remembers the definition of limit. The definition of limit is for any vector function or whatever it is, for any function, this is going to be the difference of these vectors over the delta t when delta t approaches or approximates to 0. The rate of change approaches to 0 here, which is the limit of f of t plus delta t minus f of t over delta t. If you want to see the visual representation of that, it's going to be like the vector in n-dimensional space, let's say f. I'm going to call it f1. f1 is essentially the of t plus delta t, and then f0, which is the initial position of that, and then there is some sort of hypercurve here, like this. Yeah, it can be anything. And then their difference is going to be the regular vector, n-dimensional vector, of course, delta f. So this is of t, and this is delta t plus t. And this is the degree between them. It is viable to say that, it is perfectly viable way to say that when our phi approaches 0, it is equivalent to saying that our delta f approaches to 0, and this is equivalent to saying this delta t approaches to 0 too. Now, if we take a look at this expression 1 over delta t times f of t plus delta t minus f of t, this is going to be the, well, simple vector difference, which is the vector of f1. We just need to find the difference between corresponding components, coordinates of these two vectors. So f1t plus delta t minus f1 of, again, this is the function of t, this is the scalar function, until fn t plus delta t minus fn of t, and this is gonna be transpose vector, blah blah blah, and it's multiple by the scalar value here. And this is the same, we already know that from linear algebra, from basic, matrix calculus or whatever, that this is equivalent to delta over t, and then minus f1 of t here, right? Until f1 of t plus delta t minus fn, not f1, fn of t over delta t. Now if we try to apply the limit here, applying the limit to this expression delta t, which is f of delta t plus t minus f of t, when delta t approaches to 0, this is going to be equal to the limit of the following vector, the limit of f1 t plus delta t minus f1 of t over delta t, and until fn. Again, this is the scalar function. Remember that. Keep this in mind because it will be important in a second. So here's the limit. Oh, what is this limit about? So this is the limit of each individual scalar function, and we know from the definition of the scalar function, and that its limit is essentially the derivative. Like, they are all dependent on one single scalar value. They are very simple functions that you probably covered in an elementary course of algebra or calculus in high school. So this is going to be the same thing, which is the a vector of differential f1 of over with respect to t, and then until differential of the function f of n, differential with respect to t, again, blah, blah, blah. And then this is a transpose belonging to n-dimensional hyperspace, hypervector space. Vector space is a little bit different thing, but, in a general sense, this is the hyperspace n-dimensional. We kind of proved the first very important conclusion, which follows from the definition of vector function in n-dimensional hyperspace. But there is one more, even more interesting case. We can generalize this case. Let's consider the following problem. I'm going to call it the problem 5001. Let me introduce you the function, which is not the simple one. It's going to be the function from n-dimensional vector space to m-dimensional vector space over the field of real numbers, This is not just a simple function, it's basically a linear mapping. It may be even the homomorphism, right, between two n and m-dimensional hyperspaces. In particular case, it can be a homomorphism. But what is particularly interesting here is that for any vector belonging to let's call it the vector x belonging to n-dimensional hyperspace, there exists a vector y, some vector y, which belongs to this vector Rm, because, well, let's say that this is the isomorphic linear mapping, but it's just called this way for simplicity. And then this y is defined as follows. By definition, we already know that this is the vector. What kind of vector? Well, this vector which has m components. So f1, again, of x, because this x is kind of the vector now, f2 of x until fm of x as well, where x belongs to Rn. Vector x can be represented by definition as the vector of components x1, x2 until xn, which belongs to the hyperspace Rn. All right, here where the things gets interesting, because now we can introduce the partial derivative of each component, partial derivative of each function here. And now we can apply different mappings, linear mappings, each of which is also a scalar function. f1 is a scalar function, f2 is a scalar function. But this is not the regular scalar function. This is the scalar function of multivariables. This is multivariable scalar function, which takes a vector as an input and produces one scalar from the scalar field. It produces y1, which belongs to R, y2, which belongs to R, and yn, which also because this is m, which belongs to R. Cool. And what is the result? Which results the vector y, which is defined as follows: y1, y2 until ym, which belongs to the hyperspace Rm over the field of real numbers. Cool, so this is a little bit more interesting. And what is particularly fascinating about this is that this vector can be obtained from a vector function that we discussed earlier. So there is a connection between our previous problem and this problem in the fact that we can introduce new mapping. Let's call this mapping gamma, and this gonna be the vector function which produces this vector x, this vector x based on some sort of scalar value. So let's gonna call this scalar value from any scalar value belonging to this field. We can then apply the gamma function, which produces the vector. I'm gonna call it gamma 1t, gamma 2t, gamma 3t, and then until gamma nt, but it doesn't really matter here. I'm just gonna do it for visibility. So this is the vector function which produces x, and then we're going to use this x in order to feed this vector into the vector defined on n-dimensional hyperspace, which in turn produces another vector from m-dimensional hyperspace. Why is it so complicated? You're going to see that in a moment. We know that for a simple scalar function, multivariable scalar function, let's suppose the function is defined as r on n into the scalar field, we know that we can apply the following thing. We know this is called Fréchet's differentiability, right? Fréchet's differentiability. Based on the Fréchet's differentiability, we know that kind of the total differential of the function can be written as the operator nabla of f at the specific point, at the specific vector, let's call it a, with an applied displacement vector h. So, well, this is just the Fréchet's differentiability principle, and then the actual increase, this is the linear prediction, right? This part is a linear prediction. But this part, delta f, is equal to total differential plus small o notation of second norm of displacement vector. And what is that? Well, if function r of h equals to o of small o, this is equivalent that limit of r of h over the second norm of h when h approximates to 0 equals 0. That means this function approximates to 0 faster than the norm of this vector, which means the linear prediction becomes increasingly close and increasingly more accurate to the actual increase. So this is the Fréchet's differentiability, and this function is called differentiable. So we can potentially use the same thing for the operator nabla f of a. We know by definition that this is the vector of partial derivatives f of x1 differential f of x2 until, let's say, f of xn, and each of them considered with respect to this a transpose which belongs to n. So this is sort of gradient vector. This is also called gradient vector. Gradient vector because, well, it is the vector which is collinear to a normal one on the n-dimensional hyperspace, but I'm not going to dive deep into this. Today I'm just going to focus on this practical case of our function that we introduced earlier, which is the f. And now for the f, which consists of results of f1x, by definition f2x, until fm of x transpose, which belongs to Rm over real field f. This is of x, right? Okay, and so based on the definition of derivative from the previous problem, from the previous step, we can conclude that the partial derivative of f based on the variable x, well, let's suppose xi, it is, by definition, is the vector of partial derivative of f 1xy f2 over with respect to x, y until partial derivative of fm with respect to xy. This is the derivative, the partial derivative of this vector function, linear mapping, basically. What is even more interesting is that we can define the operator nabla in the similar way. Operator nabla for particular f of j with respect to y. I'm gonna call it not the y, but gamma of t 0, gamma of t 0. This is exactly what I defined earlier here. See, this is the gamma function because we consider the specific value of this specific scalar function. This is the scalar function which takes this vector, and we apply the operator nabla. So this is by definition is the partial derivative of fj over, here it becomes interesting, over x1, partial derivative of fj over x2, and also this is from gamma t0, gamma t0, and then until partial derivative of fj xn, because we only have n different variables here, also from gamma t0. Transpose belongs to n-dimensional space in this situation. Okay, cool. And we can also note here that j is less than or equal to m, because we have maximum number of m scalar functions here. So, okay, that is interesting. We know that for a particular f, based on our Fréchet's definition, for, well, let's say one simple case, we can apply total differential in a similar way for one specific function f of j, which is taking at the specific time gamma t0, And since this part returns the linear mapping of total differential, this is the linear mapping, the algebra of linear mappings. We should apply another vector. This is going to be displacement vector with respect to y. This is going to be equal by definition, by formula, to operator nabla for this particular vector taken at the specific gamma vector defined in hyperspace N with the appropriate displacement vector HO. Cool. Now we can generalize this definition for all possible scalar products, scalar vectors. Well, in this case, this is called, I'm going to introduce a new matrix. This is going to be called Jacobian matrix. By definition, Jacobian matrix with respect to y t0 at a specific time, at a specific vector. This is the matrix, which looks like this. The operator nabla of f1 at the specific moment of time, and then operator nabla f2 at the specific point of time, and then until gradient vector of fm at the specific gamma 0 vector, which is transpose, which should be transpose, right? Which is equivalent to saying that our Jacobian matrix equals to the following representation. We know that this is the okay, so let me just remove this transpose, because this is gonna break everything. If we have to keep it as the vector column, because we're gonna transpose it afterwards, and we're gonna get the matrix that we need. So this is going to be x1 and fm here, and then what else do we have? We have f1 over partial derivative with respect to x2. Okay, sorry, I just forgot to add that this is the gamma of t0, and here it is gamma of t0, of course, f1 over partial derivative of x2 with gamma of t0 until the same fm, right? Yeah, until f1 over xm, that should be correct. Xn, sorry, we have n variables, obviously. Gamma, partial derivative of x2, again gamma, t0, until fm, xn, gamma t0. Nice, cool. So this is the matrix, which belongs to the following m to n matrix space. And we know that the total differential applied to the function f in general, taken at the specific moment of time from gamma vector with an applied respective displacement vector of y, let's say, gives us, what does it give us? Not the operator nabla, but Jacobian matrix at the specific vector gamma with the respective displacement vector. We can rewrite this as the following. This is gonna be the differential operator at the specific gamma vector in hyperspace, and this is the hyperspace n. This is the hyperspace n with a respective displacement vector y. Y is also defined in the hyperspace n, which would be the matrix f1 x1 of gamma vector until f1 fxn gamma vector m gamma vector t0 over x1 until f m xn gamma vector t0 multiplied by displacement vector h1 h2 until hn. And then from this we can conclude that the particular element of this by a simple matrix multiplication, I'm going to call this ith element, is going to be equal to the sum of partial derivative of f, I believe, I over the following, partial derivatives with respect to the following variables multiplied by h, component of the displacement vector h, take some values from 1 until n. And what is this? What is this? This is the linear prediction of change in the direction of displacement vector for a particular vector result. So we know that this one belongs to the m-dimensional hyperspace. This is the vector. This is the prediction vector. And this value, this value, which is the scalar value, this belongs to the scalar field R. This is the linear prediction of component, linear prediction of vector with a respective direction of displacement vector h, So I guess that's pretty much it. We can also write here that the actual change of the vector delta f is approximately equals to the total differential operator f gamma vector t0 with the displacement h with respect to y, and more rigorously that equals to this plus small o notation and this a second norm of the displacement vector h. So that's pretty much it. That was pretty interesting problem to show you. So there is nothing scary here, there is nothing overly complicated. So this is just Jacobian matrix. The same rules apply in hyperdimensional, n-dimensional, and m-dimensional space. So as you can see, that's decomposed in a pretty intuitive and pretty simple way. And if you break down everything into individual components, you can see what follows from where, what follows from what, and so on. I mean, that's pretty fascinating subject to study. If you have any questions, you can leave them in the comment section below. And thank you for watching.